Ladies and gentlemen, my name is Yen-Luan Chen. I am the co-author, Chen, our Associate Professor of Takming University from Taiwan. It's our pleasure to share our paper to you. The topic is Discrete Replacement Scheduling for a multi-component system with value interaction. Okay, first we consider a multi-component system consists of n different components with value interaction. Value interaction is components phenomenon in complex and large-scale industrial plants, which may cause tremendous economic losses and unacceptable safety risks. For this reason, preventive maintenance is of significant import due to its capacity in restoring the system performance and reducing the economic losses due to failures. This slide we present the system model. Consider that a multi-component system consists of n different components. Assumes that components I, which equals from 1 to n, has a value time xi with distribution fi of t, survival fi bar of t, and failure rate it, cumulative risk lambda t. Suppose that components I experience one of the two types of failures. One is type 1 failure, which is minor with probability Qi and is corrected by a minimal repair. The second is type 2 failure, which is major failure with probability Pi, which is equals to 1 minus Qi, induced instantaneous failure of the remaining components. Then the system fails and is completely replaced by a corrected replacement CR. This slide will show the definition of variable in our paper. If there is no PR is considered, let Zi be waiting time until the first type 2 value for components I, and we can find its survival function obtained as the following equation Hi bar of t, like this equation. Please refer to it. And we define Z as the time to first system CR. It is easy seeing that Z equals to minimum Zi. And then the survival function is given by this equation H bar of t. Please refer to it. If a multi-component system operates n successive random jobs, then it would be better perform the PR action after all jobs are completed. Suppose that J's working time Yj with distribution J of t survival G of t survival G bar of t. The total J's working time Sj is equal to Y1 plus from Y1 to Yj. Okay, with distribution Gj of t survival G bar J of t. The system is scheduled to perform a preventive replacement PR at completion Sn of n working jobs. And there are shortage cost and excess cost. If the PR time T is scheduled too late after the system failure, this results in a shortage cost CS times Sn minus J. And if the PR time T is scheduled too early before the system failure, this results in an excess cost CE times Z minus Sn. That the figure shows, please refers to it. This slide over the cost, corresponding cost in our paper. One, PR cost CP and the additional replacement cost due to accidents, that is CA. And CM is minimal repair cost. And so the CR cost will be CP plus CA. And the shortage cost and excess cost as shown in the above. In this paper, we pursued a number PR policy we called N policy. A number-dependent PR policy N policy for a multi-component system with value interaction is formulated and optimized. The mean cost rate function of N policy can be obtained as a following equation we called JB of N. Please refer to it. We derive optimal PR policy N star that minimize the mean cost rate JB of N. To minimize JB of N with respect to N, the optimal number N star satisfies the equalities. And the finite and unique solution N star can be shown analytically and computed numerically. This slide we present a numerical example to show our paper. Fine. Okay. Consider components I. The failure time Xi is variable distribution f of t, like this. And the working time Yi is exponential distribution g of t, like this. The following data are used for parameter as list terms, which we can see alpha is equal to 1, beta is equal to t, zeta is 1, and Cp is 215 star n, and Cn is 1000, Cs is 1 and 50, as Ci is 50, and Cn is follow normal distribution with mean 100 and standard deviation 2 and 5, 25. Okay. The optimal dependent PR policy N star and its minimal cost rate is presented in the table for fixed N from 1 to 3. Okay. And in this table, we can find the following remarks. Similar to our scientific result, Table 1 shows existence and final and the unique optimal solution for our PR policy. When minimal repair probability Q increased and the minimum mean cost rate diminished, and the optimal scheduling number n star increase. It is intuitive because because the two probability of the major value result in length PR schedule. Okay, this is the end of our presentation, and thank you for your listening.